Alright, so about normal curvature, we have this theorem that all the curves, let's stop at here. Okay. So, well, about normal curvature, we observe that all the curve on a surface which have the same line as tangent at a point, then the normal curvature, then their curvature will be same as the normal curvature. All the curves will have the same normal curvature. There is another theorem which is known as Musnier theorem. What is this spelling? S-N-E-I-R. Musnier theorem. It says that if the principal normal and the normal to the surface n, if small n and capital F have an angle alpha between them, then the normal curvature Kn is K cos alpha. It is easy to prove this theorem, and we can also realize that a small n and capital N can have any non-trivial angle between them. So, if the angle between them is alpha, then the normal curvature K n will be equal to the curvature of the curve into cosine alpha. As small n and capital N are unit vectors, n dot n will be cos alpha. So, cos alpha will be n dot n. So, am I right? And this is because of the fact that both n and n are unit vectors, and alpha is the angle between them, and Kn, and by definition Kn is nothing but K dot n. In fact, it is Kn dot n. It is Kn bar dot n bar, and Kn bar can be written as, you remember that K bar equal to Kg bar plus Kn bar, and therefore, Kn bar from here is equal to K bar minus Kg bar. Okay. And from here I can therefore write down this as K bar minus Kg bar dot n. Kg bar is a vector along u, and u is perpendicular to capital N, that is the dot product of Kg and capital N will be 0. So, this will be simply K bar dot n, and K bar is along small n. So, I can say that K into small n dot n. The vector K bar is a vector along small n. So, this is K times small n into n. N dot n you are already given is K cos alpha. It is cos alpha. So, this turns out to be cos alpha. So, that is K n equal to K cos alpha. So, this is what Musnier formula is, and this is a simple proof of this fact.
We have T and N in the plane, small
T,
n, small n in the plane, sir.
T and N, they lie in the osculating plane.
So capital N is perpendicular to the
Capital N is perpendicular to the surface.
surface, means perpendicular to the curve also, sir.
It is perpendicular to the tangent to the curve. Yes.
Sir, N will not perpendicular to this.
N has, small n has nothing to do with capital N. Small n will change the direction. I just showed you the surface. For example, look at this curve. what is the direction of small n? Will be like this, tilted, and capital N is standing like this. But for this curve, small n and capital N are collinear with each other. It depends on the curve. From curve to curve, small n will change, but capital N will always be normal to the surface. So, sometime the angle between them will be alpha, sometime they will become collinear, sometime they will be perpendicular also. It depends on the curve. Okay. So, what do you see from this formula is that Kn depends on alpha, and alpha depends on small n. Why I am saying that alpha depends on small n? Because capital N is fixed. I have no control on capital N, it is a object of the surface. So, with regard to the curve, you can say that Kn depends on alpha. In other words, Kn depends on small n. So, what follows from here? So, one of the inferences that Kn depends, or it is a function of small n, or first I will write down Kn depends on alpha, the angle between small n and capital N. Capital N is fixed for the surface, and therefore, Kn depends on small n. When I say capital N is fixed, do not get confused that it is a fixed vector. As a vector field, it is fixed. When I am discussing certain thing, I am discussing at a point. Okay. So, as a vector field, it is fixed. I have no control over it, because it is an object of the surface. We are looking at the curve only. So, Kn depends on its principal normal n. From Meusner theorem, this is the inference, and from the earlier theorem, from this theorem, we have seen that Kn depends on T. From the last theorem, this is observation number 1. From the last theorem, if you call it theorem 1, from theorem 1, we have what you have? You have that Kn depends on T. This is observation, let me call as number 2. Now, from if I combine the two observations, what will you say? Because small t and small n generate the osculating plane. So, if I combine 1 and 2, I will say that Kn depends on the osculating plane. So, combining 1 and 2, it follows that Kn depends on its osculating plane. In other words, all the curves over a surface at a point which have the same osculating plane will have the same normal curvature. All right. So, this can be written as a theorem. So, I can write down in a more formal way a theorem. This is theorem number 2. So, what we have observed over there can be stated in the form of a theorem as follows. All curves on a surface, all curves on a surface through P, through a point P, which have the same osculating plane, which have the same osculating plane through P, of course, have the same curvature K at P, have the same curvature K at P. Okay. And now there is a important section of a surface which is called the normal section. If you cut a surface by a plane, the common part will between the surface and the plane will be a curve, and that curve is called the section of the surface through this plane. If you are cutting it by a normal plane, then the curve so obtained will be called a normal section of the curve. So, normal section of the surface. So, this is the definition. A normal section at P, at a point P of a surface, of course, is the curve along which a normal plane through P, a normal plane through P cuts the surface. So, a normal plane will contain the normal capital N, and there is another normal for a curve, that is a small n. So, both of them are in the same. So, what will happen for a normal section, for a normal section, small n, the principal normal, and the capital N of the surface, they will become the same. Okay. And therefore, what will happen? Therefore, n dot n will be how much? The angle between small n and capital N becomes 0, because 0 is 1. So, n dot n will become 1, n dot n is 1, and this is, and that is why from there k n equal to k cos alpha. So, that is why I said that they have the same curvature. So, this implies k n equal to k. Okay. So, if you have a normal section of a surface, that it is a normal curvature and the curvature will become same. Okay. Now, okay. All right. So, this is an important observation. Now, I move on to the next topic, that is the principal curvatures. I do not need to write down the language all the time, because the language the students can find from the notes as well as from the books. So, I simply explain what the point is, and the language they can write down from the notes or the books. So, next thing is the principal curvatures. And when I will talk about principal curvature, there are other curvature measures that will automatically be evolved, and those curvature measures are mean curvature, and the Gaussian curvature. Okay. So, these curvature will automatically emerge. Basically, I am going to talk about the principal curvature. So, what we observed earlier while discussing the expression of the normal curvature, that it is given by B 11 plus 2 times B 12 into lambda plus B 22 into lambda square, G 11 plus 2 times G 12 lambda plus G 22 lambda square, where lambda is du 2 upon du 1. We just discussed this expression of Kn in terms of lambda. Lambda denotes the direction of the curve or the tangent of the curve. Okay. So, we can see from here that Kn depends on lambda. So, we had already observed that Kn is a function of lambda, and it is a continuous function of lambda because it is a rational function. So, it is a continuous function, and if I take a small part of the surface, then a continuous function attains its bounds. In fact, it is a differentiable function. So, the function Kn as a function of lambda will attain its bound. In other words, what I want to say is that at somewhere on the surface it will be maximum and somewhere it will be minimum. So, Kn, the maximum and minimum values of Kn are called the principal curvature. So, this you can write down as a definition. So, the maximum and the minimum values, the maximum and minimum values of the normal curvature Kn on a surface, the maximum and minimum values of the normal curvature Kn are called principal curvatures. These values will be attained because your function is a differentiable function and only on a compact part of the surface. All right, and I will be denoting these maximum and minimum values by the symbol K1 and K2. Okay. So, we denote these, we denote principal curvatures by the symbols K1 and K2. Now, in order to work them out, what we will be doing, we will be differentiating this expression of Kn, and I will put K derivative of Kn equal to 0. This will give me the maximum and minimum values, in fact K1 and K2. So, K1, K2 can be computed by putting dKn over d lambda equal to 0. So, I will differentiate this first expression of this article. So, differentiating 1 with respect to lambda, differentiating 1 with respect to lambda. So, first I will rewrite 1 as follows. So, 1 can be rewritten as G11 into plus 2 times G12 into lambda plus G22 into lambda square Kn equal to B11 plus 2B12 lambda plus B22 lambda square. So, this is also 1. These equations are same. I am differentiating this with respect to lambda. So, derivative of the bracket will be 2 times G12 plus G22 lambda. Okay. Kn as it is plus something into dkn over d lambda. This something is this bracket equal to derivative in the right side will be 2 times B12 plus B22 lambda. So, equating dkn over d lambda for k1 k2 for the maximum and minimum values, maximum and minimum values of kn, equating dkn over d lambda to 0. Okay, that will give me, so 2 is 2 will be, this will become 0. So, you will be getting G12 plus G22 lambda into Kn equal to B12 plus B22 lambda K, and this implies Kn equal to B12 plus B22 lambda upon G12 plus G22 lambda. This is number 2. Okay. All right. Now, further I can rewrite this equation number 1. Further, one can also be written as Kn equal to B11 plus B12 lambda plus lambda times B12 plus B22 lambda. Similarly, in the denominator G11 plus G12 lambda plus lambda times G12 plus G22 lambda. This I will call as number 3. Okay. 3 and 1 are same, the only difference is of writing. Now, from 2 and 3 you can see that these two things are same as this. So, if I apply componendo and dividendo rule, I will get the following. I can rub out this part, even this one. So, 2 and 3 imply that Kn is equal to B11 plus B12 lambda upon G11 plus G12 lambda. This is same as B12 lambda will be cancelled out, B12 plus B22 lambda upon G12 plus G22 lambda. Okay, so these are two equations in fact, but anyway you can call it 4. You see what componendo and dividendo rule says, that if say x equal to a upon b and this is also equal to c upon d, then you can see that x is also equal to a plus lambda c upon b plus lambda. That can be proved by adding 1 in both sides, adding scalars, and then you can. Okay, so now I will simplify the last expression. So first I will take the first and the last term together. So this implies what? B12 plus B22 lambda equal to G12 into Kn plus G22 Kn lambda. Okay. And if I take the first and second term together, I will be getting B11 plus B12 lambda equal to G11 into Kn plus G12 Kn into lambda. Okay, or I can simplify the above equation further, or I can rewrite this as B12 minus G12 Kn equal to lambda times or plus lambda times B22 minus, there was lambda also?
No, sir.
G22,
Yes, lambda.
there was lambda also. G22 into Kn equal to 0. Is it visible?
Yes, sir.
Similarly, in the next line here, I will be having B11 minus G11 into Kn and plus lambda times B12 minus G12 Kn equal to 0. Now, what I will be doing from the last two lines, this you may call it 4, 5 and 6. So, these are 5 and 6. So, I will eliminate lambda from 5 and 6, eliminating lambda between 5 and 6. See what do you get. So, what we will be doing, we will compute lambda from 5 and we will substitute into 6. Yes, so lambda from 5 will be equal to G12 Kn minus B12 upon B22 minus G22 Kn. Am I right? And this should be substituted over here. So, that will give me B11 minus G11 into Kn plus G12 Kn minus B12 upon B22 minus G22 Kn multiplied by B12 minus G12 Kn equal to 0. So, lambda is gone, or I can say, so this becomes B11 minus G11 into Kn into B22 minus G22 Kn plus this B12 minus G12. If I put a minus sign over here, these two bracket will become same. So, minus I will take common. So, this is minus times G12 Kn minus B12 whole square equal to 0. Okay. Now, this equation can be simplified and you can easily observe you are going to get a quadratic equation in Kn. This is what we expected also, because we have two values of Kn, one is maximum and minimum. So, a quadratic equation was to be formed. So, this is the quadratic equation we were looking for. So, simplification you can do, I will write down directly what you will be getting. So, this will give you G11 into G22 minus G12 square into Kn square. And okay, if you want I can simplify it, but plus or minus times I don't know. Okay, this is G times, this is also G by the way, G22 I have written directly in fact. That can be done 2 times G12 into B12 plus G11 into B11 Kn, and then plus B equal to 0. Now, this first term is in fact G. So, you can divide throughout by G. Everybody can recognize this is G. So, dividing throughout by G, this equation will become Kn square minus was there a G? I don't think there was a G here. G was not there. So, G was there? Okay. Okay, you can check it up. So, this is just G22, B22. If I want to write it in the summation form, it will be written as Gii into Bii. You can check it out. Okay. So, this is the summation. Summation is there because I is a dummy index. So, if you take a sum over I, you will be getting these terms 1 1 1 1, 1 2 1 2, 2 1 2 2 1 and 2 2 2. So, plus B upon G equal to 0. And we know what G upon Ij does. It raises the index. So, this term will become Bii into Kn plus B upon G equal to 0. So, this is a quadratic equation in Kn whose roots are K1 and K2, because you have already put dKn over d lambda equal to 0. So, the roots of this quadratic equation are K1 and K2. The roots of the above quadratic equation are K1 and K2. So, if you are interested in finding the principal curvatures, what you need to do? You need to find out the roots of this quadratic equation. That will give you the maximum and minimum values of the normal curvature, which are precisely the principal curvatures. Now, what is interesting to note over here is that the sum of the principal curvatures. So, sum of the principal curvatures, sum of the principal curvatures equal to this quantity minus times upon this. So, it will become simply Bii, that is B11 plus B22. When you will take the sum over I, it will be B11 plus B22. This is also a curvature measure, because these are the roots of a quadratic equation in normal with variable normal curvature. So, the roots will be some curvature measure. So, the sum of the curvature measure is also a curvature measure. We will call it a mean curvature of the curve. Mean curvature. So, sum of the principal curvature is called the mean curvature, and product of the curvatures, product of the roots, product of principal curvatures, it is equal to b by g. This is a known fellow, we already know it is a Gaussian curvature. So, this is the Gaussian curvature. So, in this lecture we have learned how to compute what the principal curvatures are, how to compute them, and their sum is also a known curvature called mean curvature, and their product is a known curvature called the Gaussian curvature. I stop at this point, we will continue next time tomorrow.